In the vast dark, something 4 million times heavier than our sun devours light itself. This invisible monster sits at the heart of our galaxy, controlling the dance of 400 billion stars. We'll journey to a place where time stops, where space bends like liquid, and where a single star races at 17 million miles per hour just to survive. If you're ready to explore the most extreme physics in our universe, prepare yourselves. We begin. Every night, you look up at stars scattered across the sky like diamonds on black silk. They seem random, chaotic, drifting wherever cosmic winds might push them. However, this couldn't be further from the truth. Our entire galaxy moves with clockwork precision. 400 billion stars, countless planets, and vast clouds of gas all orbit the same invisible point. Right now, our solar system hurtles through space at 515,000 miles per hour, following a path around something we cannot see. This cosmic dance takes 240 million years to complete just once. Dinosaurs roamed Earth the last time we occupied this exact spot in our galactic orbit. Yet something holds this massive spiral of matter together with gravitational chains stronger than steel. What could possibly anchor an entire galaxy? For centuries, astronomers assumed the answer was simple gravity from all the stars pulling on each other. Like dancers holding hands in a cosmic circle, stellar gravity would naturally create order from chaos. The math seemed to work. The observations seemed to fit. But when scientists actually measured how fast stars should orbit based on visible matter alone, the numbers didn't add up. Stars near the galactic edge moved far too quickly. They should have been flung into the cold darkness of space long ago. Something massive lurked at the center, something with gravitational pull so intense it could grip stars from 26,000 light-years away. This hidden anchor had to weigh millions of times more than our sun. Yet telescopes saw nothing there except empty blackness. Imagine holding a massive, invisible magnet beneath a table covered with iron filings. The metal pieces arrange themselves in perfect spirals, revealing the hidden force below. Our galaxy resembles those iron filings, organized by an invisible power at its core. The center of our galaxy lies in the direction of Sagittarius constellation, behind thick clouds of dust that block visible light. For decades, this cosmic fog kept the truth hidden from our instruments. We could see the effects, but not the cause. Radio waves, however, pierced through dust like X-rays through flesh. In the 1970s, astronomers turned their radio telescopes toward the galactic center and discovered something extraordinary. A compact source blazed with radio energy, brighter than anything else in our galaxy. They named it Sagittarius A star, marking the location with an asterisk like a warning sign. But radio waves alone couldn't reveal the true nature of this beast. What kind of object could generate such intense radiation while remaining completely invisible to every other wavelength of light? The answer would challenge everything we thought we knew about the universe itself. The universe speaks to us in many languages. Stars sing in visible light. Hot gas clouds whisper in infrared. Violent cosmic events scream in gamma rays. However, the center of our galaxy chose to communicate through radio waves, like a monster deliberately disguising its voice. In 1974, astronomers Bruce Ballack and Robert Brown aimed their radio telescope toward the constellation Sagittarius. They expected to find the usual cosmic static, the background hum of interstellar space. Instead, they discovered something that defied explanation. A brilliant radio source blazed from the exact center of our galaxy. This wasn't the gentle glow of distant stars or the scattered emissions from gas clouds. This was a focused beam of energy, concentrated into a region smaller than our solar system, yet outshining entire stellar populations. They designated it Sagittarius A star, with the asterisk symbol marking it as something unique and puzzling. But here's where the mystery deepened. When astronomers searched for this same object using visible light telescopes, they found absolutely nothing. No star, no glowing cloud, no bright disk of matter. The most powerful radio source in our galaxy had somehow made itself invisible to human eyes. Think of a person shouting loudly in a crowded room while wearing a perfect invisibility cloak. You can hear them clearly, even locate their exact position by sound alone, but you cannot see them, no matter how hard you look. Sagittarius A star presented the same paradox on a cosmic scale. Radio telescopes revealed intricate details about this hidden object. It measured roughly 12 million miles across, similar to the distance between Earth and Sun, multiplied by 130 times. The radio emissions showed structure, patterns that suggested rotation and magnetic fields of incredible strength. Yet optical telescopes saw only the black emptiness of space. The intensity of radio waves suggested enormous amounts of energy being released. Whatever process powered Sagittarius A star generated more energy in a single second than our sun produces in an entire year. This wasn't some gentle stellar fire burning in the darkness. This was a cosmic furnace of unimaginable power. Astronomers realized they were observing something fundamentally different from any known astronomical object. Not a star, because stars shine in visible light. Not a gas cloud, because the emissions were too concentrated. Not a collection of stars, because the source remained point-like, even through the most powerful telescopes. The radio signature also showed peculiar stability. While other cosmic radio sources flickered and varied over days or weeks, Sagittarius A star maintained consistent brightness year after year. This suggested an object of enormous mass, too massive to change quickly. As more radio observations accumulated, a disturbing picture emerged. The energy output required a central engine weighing millions of times more than our Sun, compressed into a space smaller than Mercury's orbit. Only one known object in the universe could fit these impossible requirements, but proving its existence would require watching the invisible monster's gravitational grip on nearby victims. Stars are supposed to move slowly through space, drifting like distant ships across the cosmic ocean. Their positions barely change over human lifetimes, creating the illusion of a fixed celestial dome above our heads. However, near the center of our galaxy, some stars move like race cars on a cosmic speedway. In the 1990s, two teams of astronomers began monitoring infrared light from the galactic center. Infrared wavelengths could penetrate the dust clouds that blocked visible observations, finally allowing us to peer into the heart of our galaxy. What they discovered shattered every assumption about stellar motion. A cluster of bright stars orbited empty space at tremendous velocities. These weren't the gentle drift patterns of normal stellar neighborhoods. These were violent, elongated orbits that carried stars millions of miles in mere months. The fastest of these stellar races became known as STU, a blue giant star following an extreme elliptical path. Every 16 years, STU completes one full orbit around nothing visible to our instruments. At its closest approach, this star reaches speeds of 17 million miles per hour. Imagine standing on STU during its closest approach. The invisible gravitational anchor would occupy half your sky, its tidal forces stretching space itself. The star's surface would glow white-hot from the intense radiation environment. Time itself would slow compared to the rest of the universe. Yet, our telescopes saw only empty blackness at the center of STU's frantic dance. The orbital mechanics told an incredible story. Something weighing 4,300,000 times more than our Sun had to exist at the precise center of these stellar orbits. The gravitational mathematics were unavoidable, locked in by centuries of Newtonian and Einsteinian physics. But this central mass occupied a space no larger than our solar system. If you tried to pack 4 million suns into the volume between Earth and Pluto, normal matter would explode outward with the force of 1 billion hydrogen bombs. No known stellar configuration could remain stable under such extreme conditions. The dancing stars revealed another crucial detail. Their orbital planes remained fixed in space, proving the central object was not a cluster of individual stars or a dense stellar core. A collection of objects would create chaotic gravitational perturbations, scrambling the orbital orientations over time. Instead, the perfect orbital stability pointed to a single, incredibly compact object. Stu's closest approach brought it within just 120 astronomical units of the invisible anchor. At this distance, the star experienced gravitational forces strong enough to bend space and time, according to Einstein's predictions. Light from Stu became redshifted as it climbed out of the deep gravitational well. These relativistic effects provided the final proof. Only one type of object in the known universe could create such extreme gravitational conditions while remaining completely invisible to telescopes. The dancing stars had revealed the location of our galaxy's ultimate predator. Now, astronomers just needed to see the monster itself. How do you weigh something you cannot see, touch, or directly observe? How do you measure an invisible giant that lurks 26,000 light-years away in the darkness of space? The answer lies in the cosmic equivalent of watching a dog chase its tail. When astronomers tracked Stu's complete orbit around the galactic center, they gained access to the most precise scale in the universe. Gravity never lies. The mathematics of orbital motion, perfected by Newton and refined by Einstein, reveal the exact mass of any central object based on how smaller objects move around it. Stu's orbit told an incredible story written in the language of physics. The star's elliptical path stretches from 970 astronomical units at its farthest point to just 120 astronomical units at closest approach. This extreme elongation creates a cosmic laboratory where gravitational effects become amplified beyond anything found elsewhere in the universe. Using these orbital measurements, astronomers calculated the central mass with extraordinary precision, 4,297,000 times the mass of our Sun, accurate to within just 12,000 solar masses. This number represents something almost impossible to comprehend. If you could somehow gather 4 million suns and crush them into a space smaller than Mercury's orbit, you would create the gravitational anchor at our galaxy's heart. But mass alone wasn't enough to solve the puzzle. The size constraint provided the final piece of evidence. Stu's closest approach places strict limits on how large the central object can be. If the invisible mass had any significant radius, Stu would eventually collide with its surface during orbit. The fact that Stu survives its closest approaches means the central object must be smaller than 120 astronomical units across. Think about the implications. 4 million solar masses compressed into a volume that would barely contain our outer solar system. The density required approaches infinity by normal standards. No known configuration of normal matter can achieve such extreme compression. If you tried to pack that much mass into such a small space using neutron star material, the densest substance known to physics, it would still collapse under its own weight. The numbers led to an inescapable conclusion. Additional evidence came from other stars in the central cluster. Star S4714 holds the record for closest approach, swooping within just 12 6/10 astronomical units of the center. That's barely farther than Saturn orbits from our Sun. At this distance, the star reaches speeds approaching 5% of the speed of light. These extreme measurements all pointed to the same answer. The gravitational anchor at our galaxy's center had to be a region of space where matter becomes so compressed that it curves space-time beyond the point of no return. The dancing stars had weighed our galaxy's central black hole with unprecedented accuracy, but seeing this invisible monster would require pushing technology to its absolute limits. For nearly 50 years after its discovery, Sagittarius A star remained a ghost. Astronomers could measure its radio emissions, track the stars that orbited it, and calculate its enormous mass, but they could never actually see the monster itself. However, in 2022, humanity finally captured the first photograph of our galaxy's central black hole. The challenge seemed impossible from the start. Black holes earn their name by trapping light so completely that no photon can escape their gravitational prison. You cannot photograph something that absorbs every wavelength of electromagnetic radiation. But black holes don't exist in perfect isolation. Matter falling toward the event horizon heats up to billions of degrees, glowing brighter than entire stars before disappearing forever. This superheated material creates an accretion disk that spirals around the black hole like water circling a cosmic drain. The Event Horizon Telescope project linked 8 radio observatories across 4 continents, creating a virtual telescope the size of planet Earth. This global array could theoretically resolve objects as small as an orange sitting on the moon's surface. Even with this incredible resolution, imaging Sagittarius A star presented unique difficulties. The black hole's relatively small size made it a challenging target, while the supermassive black hole in galaxy Messier 87 weighs 6 billion times more than our Sun. Sagittarius A star contains only 4 million solar masses. Its event horizon spans just 12 million miles, tiny by astronomical standards. The imaging process also had to account for our location within the galaxy itself. We peer at the galactic center through 26,000 light-years of interstellar dust, gas clouds, and stellar radiation. This cosmic fog blurs and distorts the image, like looking through a dirty window during a thunderstorm. The breakthrough came from combining observations taken over multiple nights. In April 2017, supercomputers spent 5 years processing the data, comparing thousands of possible images against the actual telescope measurements. The final result revealed Sagittarius A star as a glowing ring of orange light surrounding a perfectly black circular shadow. The shadow represents the event horizon itself, the boundary where space-time curves so severely that nothing can escape. The image matched Einstein's predictions with stunning accuracy. General relativity, developed more than a century ago, had perfectly described the appearance of an object that wouldn't be photographed until 2022. The glowing ring showed matter heated to 10 billion degrees as it spiraled toward oblivion. Magnetic fields twisted through the plasma, creating bright spots that raced around the black hole at nearly the speed of light. The entire ring structure rotated clockwise, revealing the spin direction of the black hole itself. This photograph represented more than just a technical achievement. For the first time in human history, we had visual confirmation that these theoretical objects actually exist in nature. The shadow cast by Sagittarius A star proved that our galaxy's central anchor really is a region where space and time break down completely. But understanding what happens near this cosmic monster required watching individual stars push the laws of physics to their breaking point. Most stars drift through space at leisurely speeds, covering just a few miles per second as they follow lazy orbits around the galactic center. These gentle velocities reflect the vast distances and weak gravitational forces that govern most cosmic motion. However, near Sagittarius A star, the normal rules of stellar movement collapse into something far more extreme. Stars 2 holds the record for the fastest confirmed orbit around any black hole. During its closest approach in May 2018, this racing star reached 7,650 kilometers per second, equivalent to 17 million miles per hour. At this velocity, Stu could travel from New York to Los Angeles in less than 1/10 of a second. The entire continental United States would flash by in the time it takes you to blink your eyes. But raw speed tells only part of the incredible story. Stu's orbital mechanics push the boundaries of what physics considers possible for normal matter. The star completes its entire 16-year journey around Sagittarius A star, while maintaining structural integrity despite experiencing gravitational forces that should tear most objects apart. During closest approach, Stu passes just 120 astronomical units from the black hole's event horizon. This distance equals roughly 11 billion miles, which sounds enormous until you consider the monster Stu is orbiting. Imagine scaling down the solar system so that Earth sits where Stu reaches its closest point. Sagittarius A star's event horizon would stretch from the Sun to beyond Jupiter's orbit, a gravitational prison 12 million miles wide. The gravitational acceleration Stu experiences at closest approach exceeds anything found elsewhere in the known universe. Tidal forces stretch the star's structure, with the side facing the black hole pulled significantly harder than the opposite side. Only Stu's enormous mass and stellar density allow it to survive these extreme conditions. The star's velocity creates relativistic effects that become measurable with current instruments. As Stu races around Sagittarius A star, its light becomes redshifted by nearly 200 kilometers per second worth of gravitational and Doppler effects combined. This redshift represents light, literally fighting to escape the black hole's gravitational well. Photons leaving Stu during closest approach lose energy as they climb out of warped space-time, becoming redder and dimmer by the time they reach Earth. Time dilation also affects Stu during its high-speed passage. Clocks on the star would run measurably slower than identical clocks in normal space. If you could somehow visit Stu during closest approach, your watch would lose several seconds compared to Earth time. The orbital period itself reveals the incredible mass concentration at the galactic center. Stu takes only 16 years to complete its entire journey around 4 million solar masses. For comparison, Pluto requires 248 years to orbit just one solar mass. This speed differential highlights the crushing gravitational intensity near Sagittarius A star. Normal stellar orbits reflect the gentle gravitational environment of typical space. Stu's frantic race reveals a region where spacetime itself has become curved to the breaking point. But even Stu's record-breaking velocity pales compared to what happens when time itself begins to stretch and warp. Time flows like a river, steady and unchanging from our human perspective. We assume that seconds tick at the same rate everywhere in the universe, that clocks on distant planets would keep perfect synchronization with timepieces on Earth. However, near Sagittarius A star, time itself becomes as twisted as the warped space around it. Einstein's general relativity makes a startling prediction about gravity's effect on time. Strong gravitational fields literally slow down the passage of time relative to weaker fields. This isn't science fiction or theoretical speculation. This is measurable physics that affects GPS satellites orbiting Earth. Near a black hole, these time dilation effects become extreme. When Stu made its closest approach to Sagittarius A star in 2018, astronomers detected exactly the gravitational redshift that Einstein's equations predicted. Light from the star became stretched to longer wavelengths as it climbed out of the black hole's gravitational well. This redshift represents more than just light changing color. It reveals that time itself runs slower in the intense gravitational field near the event horizon. Imagine you could somehow visit Stu during its closest approach, carrying a perfectly accurate atomic clock. As you descended into the gravitational well around Sagittarius A star, your clock would begin ticking more slowly compared to identical clocks on Earth. The effect wouldn't feel noticeable to you. Your biological processes would slow down by exactly the same amount as your clock, so everything would seem normal from your perspective. But observers, watching from a safe distance, would see you moving in apparent slow motion. At Stu's closest approach, this time dilation creates a measurable effect. For every million seconds that pass on Earth, Stu experiences roughly 999,999 seconds. The difference amounts to only about 10 seconds per million, but modern instruments can detect this tiny variation. The gravitational redshift grows more extreme closer to the event horizon. If you could somehow hover just outside the black hole's point of no return, time dilation would approach infinite values. Your seconds would stretch into hours as viewed from normal space. This creates one of the most bizarre consequences of black hole physics. An outside observer watching someone fall into Sagittarius A star would never actually see the person cross the event horizon. Instead, the falling victim would appear to slow down and freeze at the boundary, their image becoming redder and dimmer until it fades from view. Meanwhile, from the falling person's perspective, they would cross the event horizon in normal time and continue toward the central singularity. The disconnect between these two reference frames represents one of the deepest mysteries in modern physics. Time dilation also affects the behavior of matter spiraling into the black hole. Hot gas in the accretion disk experiences different flow rates depending on its distance from the event horizon. Material closer to the black hole moves through time more slowly than gas farther out. This differential time flow helps explain the complex dynamics visible in the first image of Sagittarius A star. But time dilation represents just the beginning of the relativistic effects that transform space near our galaxy's central monster. In the simple world of Newtonian physics, planets follow the same elliptical path over and over again. Earth's orbit around the Sun creates a perfect closed loop that repeats identically year after year for billions of years. However, near Sagittarius A star, even the concept of a stable orbit breaks down into something far stranger. Star STU doesn't follow the same path twice. Instead, its orbit precesses, meaning the entire elliptical track slowly rotates in space. Each 16-year journey around the black hole traces a slightly different route, creating a flower-like pattern called a rosette. This orbital precession represents one of the most precise tests of Einstein's general relativity ever conducted. The effect occurs because space-time near Sagittarius A star becomes so warped that the usual rules of geometry no longer apply. In flat space, the angles of a triangle always add up to exactly 180 degrees. Near a black hole, the same triangle might have angles totaling more than 180 degrees because space itself has become curved. STU's precession amounts to 12 arc minutes per orbit, roughly 1/5 of a degree. This tiny rotation accumulates over multiple orbits, causing the star's path to trace out a cosmic flower pattern over centuries of observation. The precision required to measure this effect pushes astronomical instrumentation to its absolute limits. 12 arc minutes equals roughly the apparent size of a tennis ball viewed from 100 miles away. Detecting such minute changes in stellar position requires combining observations from multiple world-class telescopes. The gravity collaboration used the 4 8-meter telescopes of the Very Large Telescope in Chile, linking them together to create a virtual instrument with the resolution of a telescope 130 meters across. This interferometric technique allowed astronomers to track STU's position with unprecedented accuracy. The measured precession matches Einstein's predictions perfectly. General relativity calculated the exact amount of orbital rotation based on the mass and spin of Sagittarius A star. When observations confirmed this prediction to within measurement error, it provided powerful evidence that our understanding of gravity remains accurate even under extreme conditions. But the rosette pattern reveals more than just relativistic physics. The precession rate depends on the total mass contained within STU's orbit. If additional massive objects lurked near the galactic center, they would alter the precession and create detectable deviations from Einstein's predictions. The fact that STU's orbit follows general relativity so precisely places strict limits on how much dark matter or other hidden mass can exist near Sagittarius A star. The black hole dominates its immediate neighborhood so completely that no other significant gravitational influences remain. The rosette dance also demonstrates the incredible stability of space-time geometry near a black hole. Despite the extreme warping of space and time, The gravitational field maintains consistent mathematical structure that allows precise predictions centuries into the future. Stu's next closest approach will occur in 2034, tracing another petal of its cosmic flower. Each orbit provides another opportunity to test the fundamental laws of physics under conditions impossible to recreate on Earth. But while Stu dances its predictable rosette pattern, Sagittarius A star itself occasionally awakens from its slumber to remind the galaxy of its tremendous power. Most of the time, Sagittarius A star sleeps quietly at the center of our galaxy, consuming matter at a gentle pace that barely registers on cosmic scales. The black hole appears almost dormant, its accretion disk glowing with the subdued light of material, slowly spiraling toward oblivion. However, 200 years ago, our galaxy's monster suddenly woke up and began to feast. NASA's imaging X-ray polarimetry explorer discovered evidence of this ancient outburst by studying X-ray light bouncing off gas clouds near the galactic center. These molecular clouds should have been cold and dark, invisible to X-ray telescopes scanning the cosmic background. Instead, they blazed with X-ray emissions so bright that astronomers initially couldn't explain the phenomenon. The breakthrough came when scientists realized they were observing an echo from the past. The X-ray light originated from Sagittarius A star during a period of intense activity roughly 200 years ago, around the beginning of the 19th century here on Earth. During this outburst, the black hole temporarily increased its brightness by factors of millions. Instead of its usual quiet consumption of interstellar gas, Sagittarius A star began devouring massive amounts of material, heating it to temperatures of billions of degrees and blasting X-ray radiation in all directions. Think of this cosmic awakening like a campfire that suddenly flares when someone throws gasoline on the embers. For most of human history, our galactic center appeared calm and stable. Then, just as Mozart was composing his final symphonies, the black hole erupted with energy that outshone entire star clusters. The X-ray pulse traveled outward at the speed of light, illuminating everything in its path. When this radiation struck nearby molecular clouds, it caused them to glow with characteristic X-ray signatures that we can still detect today. The timing works out perfectly. Light from the 200-year-old outburst has had exactly enough time to reach the molecular clouds, reflect off their surfaces, and arrive at Earth in the 21st century. This discovery revealed that Sagittarius A star's current quiet state doesn't represent its normal behavior over long timescales. The black hole undergoes periodic feeding frenzies when large amounts of material fall into its gravitational influence. What could have triggered such a dramatic awakening? Astronomers suspect that a massive gas cloud or even a disrupted star provided the fuel for this ancient feast. As the material spiraled into the black hole, it formed a temporary accretion disk, much brighter and more active than anything we observe today. The outburst also helps explain some puzzling features of the galactic center environment. High-energy particles accelerated during the event may have created some of the mysterious filamentary structures visible in radio observations. Understanding these periodic outbursts becomes crucial for predicting Sagittarius A star's future behavior. If the black hole awakened so dramatically just 2 centuries ago, it could easily do so again during human civilization's lifetime. The sleeping giant at our galaxy's heart occasionally opens its eyes to remind us of the incredible energies lurking just beneath its calm exterior. But even in its current quiet state, Sagittarius A star reveals surprising gentleness for such a massive cosmic predator. Common sense suggests that a monster weighing 4 million times more than our sun would be a voracious cosmic predator, constantly devouring everything within reach of its gravitational claws. However, Sagittarius A star turns out to be surprisingly picky about its meals. Despite sitting at the center of our galaxy with access to vast amounts of interstellar material, the black hole consumes matter at an almost leisurely pace. Current observations suggest Sagittarius A star accretes roughly 1 Earth mass of material per year. This might sound like an enormous appetite until you consider the scale involved. 1 Earth mass equals about 6 trillion kilograms, which represents less than 1/1,000,000th of 1% of the black hole's total mass. At this rate, Sagittarius A star would need to feed continuously for trillions of years just to double its current size. The reason for this surprisingly gentle behavior lies in the physics of accretion near black holes. When matter approaches the event horizon, it doesn't simply fall straight in like water down a drain. Instead, the material must lose both energy and angular momentum before it can complete its final plunge. This process requires complex interactions between magnetic fields, turbulent gas flows, and radiation pressure. Research using NASA's Chandra X-ray Observatory revealed that less than 1% of the material initially captured by Sagittarius A star's gravity actually makes it across the event horizon. The remaining 99% gets heated to extreme temperatures and ejected back into space through powerful outflows. Think of this like a cosmic filtration system. The black hole captures huge amounts of material from stellar winds and interstellar gas clouds, but its own feeding process becomes so violent that most of the matter gets blown away before reaching the point of no return. This inefficient accretion explains why Sagittarius A star appears so dim compared to supermassive black holes in other galaxies. Active galactic nuclei can outshine their entire host galaxies when matter falls into their central black holes at high rates. Our galaxy's monster, by contrast, glows with roughly the same luminosity as an ordinary star. The gentle nature of Sagittarius A star's feeding also means our galaxy avoids the dramatic consequences of an active galactic nucleus. Instead of violent jets of high-energy particles streaming from the galactic center, we observe relatively quiet radio emissions and modest X-ray output. This quiescent behavior may be temporary on cosmic timescales. When the Andromeda Galaxy collides with the Milky Way in approximately 4 billion years, the gravitational disruption will send vast amounts of gas and stars toward both galactic centers. The resulting feeding frenzy could transform our gentle giant into a blazing quasar. But for now, Sagittarius A star maintains its role as a surprisingly well-behaved cosmic citizen, powerful enough to anchor our entire galaxy, yet gentle enough to avoid disrupting the stellar neighborhoods where life might flourish. This seemingly contradictory nature reflects the complex physics governing how black holes interact with their surrounding environment. The monster at our galaxy's heart doesn't rule through brute force alone, but through the subtle choreography of gravity, magnetism, and thermodynamics operating on scales that dwarf human comprehension. From our perspective on Earth, the Milky Way appears as a faint band of light stretching across the night sky. This gentle arc seems permanent and unchanging, a fixed feature of the cosmos that has looked the same for all of human history. However, the delicate spiral structure of our galaxy exists only because of the massive gravitational anchor at its center. Sagittarius A star doesn't just passively occupy the galactic center. The black hole actively shapes the distribution of stars, gas clouds, and dark matter across hundreds of thousands of light years. Like a cosmic sculptor working with materials of unimaginable scale, it carves our galaxy's elegant spiral arms through pure gravitational influence. The process begins with density waves that propagate outward from the galactic center. These gravitational ripples travel at different speeds than the orbital motion of stars, creating regions where stellar material becomes compressed into the bright spiral patterns we observe. Think of cars merging onto a crowded highway. Traffic naturally bunches up in certain areas while remaining sparse in others, creating waves of congestion that move at different speeds than individual vehicles. Our galaxy's spiral arms form through similar dynamics, with Sagittarius A star providing the gravitational equivalent of highway on-ramps and off-ramps. The black hole's influence extends far beyond simple gravitational attraction. magnetic field lines threading through the galactic center get twisted and amplified by the rotation of matter around Sagittarius A star. These magnetic fields then guide the motion of charged particles and ionized gas throughout the galaxy. Recent observations have revealed enormous magnetic field structures stretching thousands of light years from the galactic center. These cosmic magnetic highways channel energy and matter between the central black hole and the outer spiral arms, creating a vast circulation system that maintains galactic structure over billions of years. Sagittarius A star also acts as a cosmic timekeeper, setting the rhythm for star formation cycles throughout the galaxy. Periodic changes in the central gravitational field send waves of compression through the galactic disk, triggering bursts of star formation that propagate outward like ripples on a cosmic pond. The black hole's mass determines many fundamental properties of our galaxy. Astronomers have discovered a tight correlation between the masses of supermassive black holes and the stellar bulges of their host galaxies. This relationship suggests that black holes and galaxies grow together through a complex feedback process. If Sagittarius A star were significantly more or less massive, our entire galaxy would have evolved differently. A lighter black hole might have allowed the Milky Way to develop into a dwarf galaxy with irregular structure. A heavier central mass could have created a more compact elliptical galaxy with little ongoing star formation. The current mass of our galactic anchor represents a cosmic Goldilocks zone, neither too big nor too small, but just right for creating the kind of spiral galaxy where solar systems like ours can form and remain stable for billions of years. This delicate balance between destruction and creation defines the relationship between Sagittarius A star and the galaxy it governs. But our black hole doesn't rule alone in the crowded neighborhood of the galactic center. The region around Sagittarius A star might seem like a cosmic wasteland, a place too dangerous for any normal astronomical objects to survive the intense gravitational and radiation environment. However, the galactic center actually teems with exotic companions that make it one of the most crowded neighborhoods in our galaxy. Within just 3 light years of the central black hole, astronomers have identified thousands of individual stellar objects. These aren't ordinary stars following safe orbits in the galactic suburbs. These are cosmic extremophiles, objects that have somehow adapted to survive in the most violent environment our galaxy has to offer. The most dramatic discovery came in November 2004, when astronomers detected GCIRS 13e, an intermediate mass black hole containing 1,300 times the mass of our Sun. This smaller monster orbits Sagittarius A star from a distance of 3 light years, accompanied by a cluster of 7 massive stars. Think of this system like a cosmic moon. Just as our moon orbits Earth while Earth orbits the Sun, GCIRS 13e follows its own orbital path around the supermassive black hole while maintaining gravitational control over its stellar companions. The existence of intermediate mass black holes near galactic centers supports theories about how supermassive black holes grow over cosmic time. Instead of forming directly from collapsed stars, monsters like Sagittarius A star may have grown through cannibalistic mergers with smaller black holes that wandered too close to the galactic center. But GCIRS 13e represents just the tip of the iceberg in terms of exotic galactic center residents. Astronomers estimate that thousands of stellar mass black holes, neutron stars, and white dwarf stars orbit within the central region. These dense stellar remnants formed when massive stars reached the end of their nuclear burning cycles and collapsed under their own gravity. The gravitational field of Sagittarius A star acts like a cosmic vacuum cleaner, capturing these dense objects and preventing them from escaping to the outer galaxy. Over billions of years, this process has concentrated an entire population of extreme stellar remnants in the galactic center. Some of these objects follow highly elongated orbits that bring them dangerously close to the central black hole, When a stellar remnant passes within a few dozen astronomical units of Sagittarius A star, tidal forces begin to strip matter from its surface, creating temporary flares of X-ray emission. The crowded environment also leads to occasional close encounters between stellar remnants themselves. When two neutron stars or black holes pass near each other, they can form binary systems that slowly spiral together while emitting gravitational waves. Recent observations have also revealed populations of very young, massive stars in the galactic center. These hot, blue giants somehow formed despite the disruptive environment near Sagittarius A star. Their presence suggests that star formation can occur even under the most extreme cosmic conditions. The youth of these stars presents a puzzle. Massive stars burn through their nuclear fuel in just a few million years, which means they must have formed recently in cosmic terms. But the intense radiation and tidal forces near the galactic center should prevent the gravitational collapse of gas clouds into new stars. Astronomers suspect these young stars formed farther from the galactic center and then migrated inward through dynamical interactions with other stellar objects. This bustling cosmic metropolis around Sagittarius A star creates a unique laboratory for studying physics under extreme conditions that cannot be replicated anywhere else in the observable universe. But sometimes, the monster at the center of this cosmic city briefly opens its eyes and reminds everyone of the incredible energies lurking beneath its calm exterior. Most astronomical objects change slowly over human timescales. Stars burn steadily for millions or billions of years. Planets follow predictable orbits. Even violent events like supernovae typically unfold over months or years from initial explosion to final fade out. However, Sagittarius A star occasionally produces flashes of energy that transform it from a sleeping giant into a blazing beacon in mere hours. On May 13, 2019, astronomers using the Keck Observatory witnessed something extraordinary. The black hole suddenly became 75 times brighter than normal in infrared wavelengths, creating the most dramatic flare ever recorded from our galactic center. The brightening happened so rapidly that astronomers initially suspected equipment malfunction. Infrared detectors recorded Sagittarius A star's luminosity increasing from its usual subdued glow to brilliant intensity in less than 2 hours. The peak brightness rivaled some of the most luminous stars in our galaxy. But this wasn't a telescope error. Multiple independent observatories confirmed the dramatic flare, capturing time-lapse images that showed the galactic center pulsing like a cosmic lighthouse. The energy output during peak brightness exceeded the black hole's normal luminosity by factors that strained theoretical models. Whatever process powered this flare released more energy in a few hours than our sun produces in several years. Astronomers suspect the flare resulted from a close encounter between Sagittarius A star and another astronomical object. The leading candidate is a massive gas cloud designated G2, which passed near the black hole around the time of the brightening event. As G2 approached the event horizon, tidal forces began shredding the cloud into streamers of hot gas. This material formed a temporary accretion disk around the black hole, heating to temperatures of billions of degrees and emitting intense radiation across the electromagnetic spectrum. The flare also revealed the incredible speed of physical processes. Near the event horizon, hot gas clumps in the accretion disk raced around Sagittarius A star at roughly 30% the speed of light, completing entire orbits in just minutes. These orbital motions became directly visible through a technique called very long baseline interferometry. By combining observations from multiple radio telescopes separated by thousands of miles, astronomers achieved the resolution needed to track individual hotspots as they whirled around the black hole. The rapid variations in brightness also provided new insights into the structure of space-time near the event horizon. As hot gas orbits close to a black hole, relativistic effects cause the light to be beamed, focused, and redshifted in patterns that depend on the exact geometry of warped space. The 2019 flare represented just the most dramatic example of Sagittarius A star's variable behavior. Smaller flares occur regularly, suggesting that the black hole maintains a more active accretion process than previously thought. These brightness variations also affect the surrounding environment. Enhanced radiation from flares can ionize gas clouds throughout the galactic center, creating temporary changes in radio and X-ray emissions from the broader region. Understanding flare mechanisms becomes crucial for predicting how Sagittarius A star might behave in the future. If relatively small disturbances can trigger such dramatic brightening events, larger disruptions could potentially transform our quiet galactic center into something resembling the active nuclei found in other galaxies. The sleeping monster occasionally reminds us that immense energies lie just beneath its calm exterior, waiting for the right conditions to illuminate our galaxy's heart with the fury of 4 million captive suns. Now, astronomers have found ways to photograph even the darkness itself. Photographing a black hole seems like the ultimate contradiction. These cosmic monsters earn their name by trapping light so completely that no photon can ever escape their gravitational prison. However, darkness itself can cast a shadow. The breakthrough that enabled the first image of Sagittarius A star came from realizing that black holes don't exist in perfect isolation. The event horizon acts like a cosmic silhouette, blocking light from the glowing matter behind it. When the Event Horizon Telescope captured its historic image in 2022, it revealed Sagittarius A star as a ring of brilliant orange light surrounding a perfectly circular shadow. The shadow represents the event horizon itself, the boundary where space-time becomes so warped that light cannot escape. This shadow measures roughly 12 million miles across, about the same as the distance from Earth to the Sun multiplied by 130 times. Yet from our perspective, 26,000 light-years away, this enormous structure appears smaller than an orange sitting on the moon's surface. The glowing ring around the shadow shows matter heated to temperatures exceeding 10 billion degrees. This superheated plasma spirals around the black hole at nearly the speed of light, creating the brightest natural phenomenon in our galaxy. Magnetic fields threading through this hot gas create bright spots that race around the event horizon like cosmic headlights. These hot spots complete full orbits in mere minutes, allowing astronomers to directly observe matter moving at relativistic speeds. The image also revealed the spin direction of Sagittarius A star itself. The glowing ring appears brighter on one side due to relativistic beaming effects. Light from gas moving toward Earth becomes amplified, while light from gas moving away appears dimmed. Creating this image required unprecedented international cooperation. 8 radio telescopes on 4 continents synchronized their observations to create a virtual telescope the size of planet Earth. The data from this global array filled thousands of computer hard drives. Processing the observations took 5 years of supercomputer calculations. Algorithms had to account for atmospheric distortions, instrumental effects, and the complex physics of light bending around curved space-time. The final result provided visual confirmation of Einstein's predictions about black hole appearance. General relativity, developed more than a century before black hole photography became possible, perfectly described the shadow size and ring structure. But the image revealed more than just pretty pictures. The precise measurements of shadow diameter confirmed the mass of Sagittarius A star to incredible accuracy. Any deviation from Einstein's predictions would have shown up as changes in the shadow size or ring brightness. The photograph also validated decades of theoretical work on accretion disk physics. The brightness patterns and hotspot motions matched computer simulations of matter falling into rotating black holes. This historic image represents humanity's first direct view of the point where space and time break down completely. The circular shadow marks the boundary beyond which our understanding of physics reaches its ultimate limit. Imagine standing at the edge of a cliff where the ground suddenly drops away into infinite darkness. You can step backward to safety, but one step forward commits you to an irreversible fall. However, The event horizon around Sagittarius A star creates something far more absolute than any physical cliff. The event horizon represents the boundary in space where the escape velocity equals the speed of light. Inside this spherical surface, nothing can move fast enough to overcome the black hole's gravitational pull. Not rockets, not light beams, not even information itself. For Sagittarius A star, this point of no return spans 12 million miles in diameter. If you could somehow replace our Sun with this event horizon, the boundary would stretch past the orbit of Venus and nearly reach Earth. Yet, despite its enormous size, the event horizon possesses no physical substance. It's not a wall or barrier made of matter. Instead, it represents a mathematical surface in space-time where the geometry of the universe fundamentally changes. Crossing the event horizon creates the ultimate one-way journey. Once inside, every possible future path leads inexorably toward the central singularity. You could fire rocket engines at maximum power, but instead of escaping, you would simply reach the center slightly faster. The mathematics of general relativity make this fate unavoidable. Inside the event horizon, the roles of space and time become interchanged. Moving toward the singularity becomes as inevitable as moving forward through time in normal space. Think of trying to travel backward in time. No matter what you do, seconds continue ticking forward into the future. Inside a black hole, approaching the singularity becomes equally unstoppable. The event horizon also creates a cosmic censorship effect. Any information that crosses the boundary becomes permanently hidden from the outside universe. If you fell past the event horizon while shouting important secrets, those secrets would be lost forever to external observers. This information barrier makes black holes fundamentally different from other astronomical objects. You can study stars by analyzing their light, probe planets with spacecraft, and understand galaxies through electromagnetic observations. But black hole interiors remain forever unknowable. The horizon's size depends entirely on the black hole's mass. Stellar mass black holes have event horizons just a few miles across. Intermediate mass black holes span hundreds of miles. Supermassive monsters like Sagittarius A star create horizons larger than planetary orbits. Strangely, the average density inside the event horizon actually decreases for more massive black holes. While a stellar mass black hole packs tremendous density into a small volume, Sagittarius A star's interior density resembles that of ordinary water. This counterintuitive relationship occurs because volume grows faster than mass as black holes increase in size. The event horizon area grows as the square of mass, making supermassive black holes less dense on average than their smaller cousins. But density measurements become meaningless at the event horizon itself. The boundary represents a place where classical physics acknowledges its own limitations. Beyond this cosmic point of no return lies a realm where the familiar rules of cause and effect break down completely. Falling toward any massive object creates tidal forces. The moon's gravity pulls slightly harder on Earth's oceans than on the solid ground beneath them, creating the twice-daily rhythm of high and low tides that has shaped coastal life for billions of years. However, near Sagittarius A star, these same tidal forces become instruments of cosmic destruction. The process begins subtly. As you approach the black hole feet first, gravity pulls slightly harder on your feet than on your head. The difference amounts to just fractions of a percent initially, barely noticeable compared to normal variations in gravitational field strength. But the tidal gradient grows exponentially steeper as you get closer. Your feet experience increasingly stronger gravitational acceleration than your head. Meanwhile, the left and right sides of your body get pulled toward the black hole's center, creating compression forces perpendicular to the stretching. This combination of vertical stretching and horizontal squeezing transforms objects into long, thin shapes, resembling strands of spaghetti. Physicists call this gruesome process spaghettification. though the technical term tidal disruption sounds more dignified. The mathematics of tidal forces depend critically on the black hole's mass. For stellar mass black holes weighing just a few times more than our Sun, spaghettification becomes lethal long before reaching the event horizon. Your body would be torn apart while the black hole still appeared as just a bright star in the distance. Sagittarius A star presents a dramatically different scenario because supermassive black holes have event horizons much farther from their centers. The tidal gradient at the point of no return remains relatively gentle. You could cross Sagittarius A star's event horizon without experiencing immediately fatal tidal forces. This doesn't mean you would survive the experience. The tidal forces continue growing stronger as you approach the central singularity. Eventually, the stretching and compression would overcome the molecular bonds holding your body together, but the process would unfold over minutes or hours, rather than the instantaneous destruction near smaller black holes. The exact point where tidal forces become fatal depends on the strength of the object being disrupted. Solid rock can withstand greater tidal stress than liquid water. Steel cables resist stretching better than biological tissue. Even massive stars can be disrupted by tidal forces when they wander too close to supermassive black holes. Astronomers have observed stellar tidal disruption events in other galaxies, creating brilliant flares as star material gets shredded and heated during its death spiral. The disrupted stellar material doesn't disappear immediately. Instead, it forms long streamers that continue orbiting the black hole while gradually spiraling inward. These stellar remnants create temporary accretion disks that can outshine entire galaxies for months or years. Tidal disruption also affects the rotation of falling objects. The differential gravitational forces create torques that can spin up objects to incredible rotation rates before they get completely shredded. Near Sagittarius A star, even the concept of fatal tidal forces becomes relative. The stretching process would render human survival impossible long before reaching the singularity, but the experience would unfold in a surreal ballet of slowly increasing distortion rather than sudden, violent destruction. However, the story becomes even stranger when viewed from different perspectives in warped space-time. Reality near a black hole depends entirely on your point of view. The same physical process can appear completely different to observers in different reference frames, creating one of the most mind-bending aspects of extreme gravity. However, this isn't just theoretical speculation. The disconnect between perspectives becomes measurably real near Sagittarius A star. Imagine watching someone fall into the black hole from a safe distance. As they approach the event horizon, time dilation causes them to appear to slow down dramatically. Their movements become sluggish, their clock ticks more slowly, and their light becomes increasingly redshifted. From your external perspective, the falling person never quite reaches the event horizon. Instead, they appear to freeze at the boundary, becoming redder and dimmer until they fade from view. Their image gets compressed into an infinitesimally thin layer just outside the point of no return. This creates what physicists call pancaking or Spaghettification. The external observer sees the falling person flattened into a two-dimensional pancake, stuck at the event horizon for eternity. But here's where the paradox becomes truly bizarre. From the falling person's perspective, nothing unusual happens during the crossing. Their clocks continue ticking at normal rates. They pass through the event horizon in finite time and continue falling toward the singularity. They experience the stretching of spaghettification, not the compression of pancaking. Both perspectives are equally valid according to general relativity. There's no correct viewpoint that resolves the contradiction. The mathematics of curved spacetime simply gives different answers depending on which coordinate system you choose for calculations. This paradox reveals fundamental limitations in how we think about reality near black holes. Classical physics assumes that events either happen or they don't, regardless of who observes them. Near event horizons, this assumption breaks down completely. The falling person both crosses the horizon and doesn't cross it simultaneously. They experience both spaghettification and pancakification. They both reach the singularity and remain frozen at the boundary forever. These contradictory descriptions aren't errors in the theory. They represent the actual nature of space-time geometry near black holes. Reality itself becomes observer-dependent in ways that challenge our deepest assumptions about the universe. The pancake paradox also has implications for information storage near black holes. If external observers see all infalling matter compressed into a thin layer at the event horizon, perhaps information about the interior gets encoded on the boundary surface itself. This idea led to the holographic principle, which suggests that all information about a volume of space might be contained on its boundary. The interior of a black hole could be entirely described by information stored on the event horizon, like a cosmic hologram. But the paradox creates additional puzzles. If you're pancaked from an external perspective, but spaghettified from your own perspective, which version of you contains your consciousness and memories? Some physicists argue that the external observer's pancaked version represents the real you, while the spaghettified version falling toward the singularity is just a mathematical artifact. Others claim the opposite. The resolution may require a complete theory of quantum gravity that doesn't yet exist. Until then, the pancake paradox stands as one of the deepest mysteries about the nature of reality itself. Near Sagittarius A star, even the concept of what happens becomes fundamentally ambiguous. Every particle in the universe carries information. An electron has charge, spin, and mass. A photon has frequency and polarization. Even the quantum state of empty space contains information about virtual particles flickering in and out of existence. However, black holes seem to destroy information completely, creating one of the most profound puzzles in modern physics. When matter falls into Sagittarius A star, it carries detailed information about its structure, composition, and quantum state. This information includes everything from the arrangement of atoms to the precise quantum mechanical properties of individual particles. Classical physics assume this information simply gets crushed at the central singularity and disappears forever. The outside universe loses access to these details, but the information itself still exists somewhere inside the black hole. But quantum mechanics tells a different story. In the 1970s, Stephen Hawking discovered that black holes actually evaporate through quantum effects near the event horizon. Virtual particle pairs constantly appear near the boundary, with one particle falling in, while the other escapes as Hawking radiation. This creates a fundamental contradiction. If black holes completely evaporate through Hawking radiation, what happens to all the information that fell in during their lifetimes? Quantum mechanics demands that information cannot be truly destroyed, only transformed or hidden. The information paradox becomes even more puzzling when you consider the properties of Hawking radiation itself. This radiation appears to be completely random, carrying no information about what fell into the black hole previously. It's like burning a library and expecting to reconstruct the books from the heat and smoke. Yet the conservation of information represents one of the most fundamental principles in quantum mechanics. Violating this principle would undermine the mathematical foundation of quantum theory and potentially break the laws of thermodynamics. Several proposed solutions attempt to resolve this paradox, each with dramatic implications for our understanding of reality. The holographic principle suggests that information never actually enters the black hole interior. Instead, it gets encoded on the event horizon surface like a cosmic hard drive. The interior of the black hole becomes a holographic projection of information stored on the boundary. Another possibility involves quantum entanglement between the infalling matter and the Hawking radiation. As particles fall into the black hole, they might remain quantum mechanically connected to the radiation being emitted, allowing information to slowly leak back out. Some physicists propose that the event horizon itself doesn't exist as a sharp boundary. Instead, quantum effects create a firewall that incinerates anything approaching the black hole, preventing information from crossing the would-be event horizon in the first place. The most radical solution suggests that space-time itself might be an emergent property of quantum entanglement. In this view, the interior of a black hole doesn't exist as a separate region of space, but rather as a complex pattern of quantum correlations. Recent theoretical work points toward information being preserved through subtle correlations in the Hawking radiation. While individual photons appear random, the collective pattern might encode complete information about everything that ever fell into the black hole. For Sagittarius A star, resolving the information paradox has practical implications. The black hole contains information about every star, gas cloud, and particle that has crossed its event horizon over the past billions of years. If this information somehow survives in the Hawking radiation, future civilizations might theoretically reconstruct the complete history of our galactic center. But understanding how information escapes requires solving mysteries that push the boundaries of physics itself. Black holes represent the ultimate cosmic prisons, trapping matter and energy so completely that nothing can escape their gravitational embrace. This simple description defined our understanding of these objects for decades after their theoretical prediction. However, in 1974, Stephen Hawking discovered that even the most perfect prison occasionally releases its captives. The breakthrough came from applying quantum mechanics to the curved space-time near event horizons. Quantum theory predicts that empty space isn't truly empty, but constantly bubbles with virtual particle pairs that appear and disappear in fractions of a second. Near a black hole's event horizon, these virtual particles can become separated before they have time to annihilate each other. One particle falls into the black hole, while its partner escapes to infinity, becoming real radiation in the process. This Hawking radiation causes black holes to slowly evaporate, like cosmic ice cubes. The temperature of Hawking radiation depends inversely on the black hole's mass. Smaller black holes glow hotter than larger ones, creating a cosmic thermostat that defies intuition. Stellar mass black holes have temperatures of just a few billionths of a degree above absolute zero. Sagittarius A star, with its enormous mass of 4 million suns, has a Hawking temperature of roughly 15 trillionths of a degree. This makes it colder than the cosmic microwave background radiation left over from the Big Bang. At such frigid temperatures, Sagittarius A star absorbs more energy from space than it emits through Hawking radiation. The black hole actually grows slightly larger by absorbing photons from the cosmic background, even without consuming additional matter. This situation will reverse in the far future as the universe continues expanding and cooling. Eventually, the background temperature will drop below the Hawking temperature of supermassive black holes, allowing them to begin their slow evaporation process. The timescales involved stretch beyond human comprehension. Sagittarius A star will require approximately 10 to the 97th years to completely evaporate through Hawking radiation. This duration exceeds the current age of the universe by factors of trillions upon trillions. During most of this evaporation process, the black hole will remain virtually unchanged. The real fireworks begin only during the final moments, when the remaining mass drops to just a few solar masses. At this point, the Hawking temperature skyrockets, causing the black hole to explode in a brilliant flash of gamma rays. The power output during the final second equals roughly 10 billion times the luminosity of our sun. All the mass that fell into the black hole over cosmic history gets converted back into pure energy and released in this ultimate cosmic firework. But Hawking radiation creates theoretical puzzles that remain unsolved. The radiation appears to carry no information about what fell into the black hole, seemingly violating the quantum mechanical principle that information cannot be destroyed. Recent theoretical work suggests that information might be encoded in subtle correlations between Hawking radiation particles. While individual photons appear random, the collective pattern might preserve complete details about the black hole's contents. For now, Hawking radiation from Sagittarius A star remains far too weak to detect with current technology. The few particles per second escaping from our galaxy's central black hole get completely swamped by radiation from normal astronomical sources. But this faint quantum glow represents the only known mechanism that allows black holes to eventually return their contents to the universe. However, some physicists question whether this gentle evaporation process can actually occur without creating paradoxes that tear apart space-time itself. Quantum mechanics and general relativity represent the two pillars of modern physics. Each theory has passed every experimental test with remarkable precision. Yet near black holes, these fundamental theories appear to contradict each other in ways that threaten our understanding of reality itself. However, the Firewall paradox suggests the contradiction might be even more dramatic than previously imagined. The puzzle begins with quantum entanglement, a phenomenon where particles become connected in ways that transcend normal space and time. When two particles become entangled, measuring one instantly affects the other, regardless of the distance separating them. Near black hole event horizons, Hawking radiation creates entangled particle pairs. One particle falls into the black hole, while its quantum twin escapes as radiation. This entanglement connection should persist even after the particles separate. But here's where the paradox emerges. Quantum mechanics also demands that Hawking radiation particles become entangled with previously emitted radiation to preserve information about the black hole's contents. This creates a fundamental conflict because quantum theory prohibits any particle from being maximally entangled with two different systems simultaneously. The principle of monogamy of entanglement forces a choice. Either the escaping Hawking particle remains entangled with its infalling partner, or it becomes entangled with previous radiation to preserve information. It cannot do both. Resolving this contradiction may require abandoning one of three sacred principles of physics. Einstein's equivalence principle states that falling freely in a gravitational field feels identical to floating in empty space. Unitarity requires that quantum information remains conserved. Local quantum field theory demands that physics works the same way in small regions everywhere. The Firewall solution proposes abandoning the equivalence principle. Instead of experiencing normal free fall across the event horizon, in falling, observers encounter a wall of high-energy particles that instantly incinerates them. This firewall would exist just inside the event horizon, invisible to outside observers, but deadly to anyone attempting to cross the boundary. The wall consists of highly energetic Hawking radiation particles that break their entanglement with infalling partners, preserving information conservation at the cost of destroying the smooth space-time geometry near the horizon. Think of approaching Sagittarius A star under Firewall theory. From a safe distance, the black hole appears normal, with matter smoothly crossing the event horizon according to general relativity. But any attempt to follow this matter across the boundary results in immediate destruction by quantum flames. The Firewall paradox reveals deep tensions between quantum mechanics and gravity that may require a complete theory of quantum gravity to resolve. String theory, loop quantum gravity, and other approaches to unifying physics all make different predictions about what happens at event horizons. Some physicists argue that firewalls represent an artifact of trying to apply quantum mechanics in regions where it doesn't belong. Others claim that information never actually crosses event horizons, making the entire paradox irrelevant. The debate has practical implications for understanding Sagittarius A star. If firewalls exist, the black hole's interior becomes fundamentally different from the smooth, curved space-time predicted by general relativity alone. Recent theoretical work suggests that the firewall paradox might resolve itself through subtle effects in quantum gravity that we don't yet understand. The mathematics becomes so complex near event horizons that definitive answers may remain beyond current computational capabilities. For now, the firewall dilemma stands as a reminder that our understanding of black holes remains incomplete. The boundary between quantum mechanics and gravity continues to hide secrets that challenge the foundations of physics itself. But even without solving these deep theoretical puzzles, black holes warp spacetime in ways that create observable effects throughout the universe. Space and time seem fixed and absolute from our everyday perspective. Distances remain constant. Angles in triangles add up to 180 degrees, and parallel lines never meet. These geometric truths appear as fundamental as mathematics itself. However, near Sagittarius A star, even the basic structure of space and time becomes twisted beyond recognition. Einstein's general relativity revealed that massive objects warp the fabric of space-time, like bowling balls placed on a stretched rubber sheet. This warping creates what we experience as gravitational attraction, with objects following the straightest possible paths through curved geometry. Near supermassive black holes, this warping reaches extreme levels that transform the entire nature of reality. Light rays that should travel in straight lines get bent into curved paths around Sagittarius A star. This gravitational lensing effect acts like a cosmic magnifying glass, focusing and distorting images of objects behind the black hole. If you could somehow position yourself at the right distance from Sagittarius A star, you might see multiple images of the same star simultaneously. Light from the star would follow different curved paths around the black hole, creating a cosmic hall of mirrors effect. The warping also affects the flow of time itself. Clocks near the black hole run slower than identical clocks in normal space. This time dilation becomes so extreme near the event horizon that time effectively stops from an external perspective. Space itself gets stretched and compressed in complex patterns around rotating black holes. The dragging of space-time by the black hole's spin creates regions where nothing can remain stationary relative to distant stars. Even light beams get swept along by the rotating geometry. This frame-dragging effect extends far beyond the event horizon, influencing the motion of matter throughout the galactic center region. Gas clouds and stellar orbits show signatures of being twisted by Sagittarius A star's rotation. The extreme warping near black holes also creates closed time-like curves, theoretical paths through space-time that loop back to their own starting points in time. Following such a path would theoretically allow travel to your own past, creating paradoxes that challenge causality itself. But the most dramatic warping occurs at the photon sphere, a region just outside the event horizon where light rays can orbit the black hole indefinitely. At this distance, the curvature of space-time perfectly balances the outward motion of light, creating stable circular orbits for photons. If you could somehow hover at the photon sphere and look sideways, you would see the back of your own head. Light from your face would travel all the way around the black hole and return to your eyes, creating the ultimate cosmic selfie. The warping also affects the apparent size and shape of the black hole itself. The event horizon appears larger than its actual size due to gravitational lensing effects that focus light from the far side of the black hole toward observers. This explains why the first image of Sagittarius A star shows a shadow roughly 2.5 times larger than the actual event horizon. The warped space-time acts like a magnifying lens that enlarges the silhouette of darkness against the glowing accretion disk. Understanding space-time warping around black holes provides insights into the fundamental nature of gravity itself. These extreme environments serve as cosmic laboratories for testing Einstein's equations under conditions impossible to recreate on Earth. But even more bizarre effects emerge when considering what external observers see during the final moments of black hole encounters. Time flows like a river in normal space, carrying events from past to future at a steady, predictable rate. We assume that processes unfold at the same pace everywhere in the universe, that distant civilizations experience the same rhythm of seconds, minutes, and hours. However, near Sagittarius A star, time itself becomes stretched to the breaking point. As matter approaches the event horizon, gravitational time dilation causes it to appear to slow down from the perspective of distant observers. This effect grows stronger with proximity to the black hole, eventually approaching infinite time, stretching at the boundary itself. The mathematics become staggering. At just 1 millimeter above the event horizon of Sagittarius A star, time passes roughly 10% slower than in normal space. At 1 micrometer above the boundary, time dilation reaches factors of hundreds. At distances measured in atomic diameters, time effectively stops. This creates one of the most haunting aspects of black hole physics. External observers never actually see anything cross the event horizon. Instead, infalling objects appear to slow down and freeze at the boundary, their images becoming redder and dimmer until they fade from view. Your last second falling into Sagittarius A star would appear to last forever to someone watching from Earth. Your final heartbeat would stretch across centuries. Your last thought would unfold over millennia. The light from your body during this final approach would become increasingly redshifted as it climbs out of the deepening gravitational well. First, your visible appearance would shift toward red wavelengths, then infrared. Eventually, the light would stretch to radio waves so long they could span entire continents. But the energy of these photons would simultaneously decrease due to the gravitational redshift. The same process that stretches the wavelength also drains the photon's energy, making your image progressively fainter as well as redder. From the perspective of distant observers, you would appear to fade gradually into darkness while frozen at the event horizon. Your last photons would continue arriving at Earth for millions or billions of years, each one redder and weaker than the last. This creates a cosmic fossil effect. Every piece of matter that has ever approached Sagittarius A star leaves a permanent imprint just outside the event horizon, frozen in time from external perspectives. The boundary becomes a repository of images, showing everything the black hole has consumed over its entire history. If you could somehow observe the event horizon with perfect instruments, you might see the ghostly images of the first stars that formed our galaxy, still apparently falling toward the black hole billions of years after their actual destruction. The frozen moment effect also means that external observers can never witness the complete evaporation of black holes through Hawking radiation. As the black hole shrinks, its surface gravity increases, causing even more extreme time dilation that prevents observers from seeing the final explosive moment. From outside perspectives, black holes become eternal objects that never quite finish forming and never completely evaporate. They exist in a perpetual state of almost, but not quite, reaching their final configurations. This temporal paradox challenges our understanding of causality and the flow of time itself. Events that definitely occur from one perspective remain forever pending from another viewpoint. The frozen moment represents the ultimate collision between general relativity and human intuition about the nature of time and causality. Beyond the event horizon of Sagittarius A star lies a realm that no information can ever describe to the outside universe. Once matter crosses this boundary, its fate becomes permanently hidden behind an impenetrable veil of warped space-time. However, general relativity still makes precise predictions about this unknowable journey. From the perspective of someone falling through the event horizon, the crossing happens in finite time with no dramatic physical effects. The boundary itself has no substance, no wall or barrier to mark the transition. You would pass through while feeling only the gentle acceleration of free fall. but your future options become fundamentally limited. Every possible path through space-time now leads inexorably toward the central singularity. No amount of rocket thrust could reverse your trajectory or allow escape back to the external universe. The mathematics of curved space-time make this fate unavoidable. Inside the event horizon, the roles of space and time become partially exchanged. Moving toward the center becomes as inevitable as moving forward through time in normal space. Think of trying to travel backward in time. No matter what actions you take, seconds continue ticking forward into the future. Inside, a black hole approaching the singularity becomes equally unstoppable. The journey inward reveals increasingly strange effects as space-time curvature grows stronger. Tidal forces that were gentle at the event horizon begin stretching your body more dramatically. The difference in gravitational pull between your head and feet increases exponentially with each passing moment. Light rays that entered the black hole simultaneously with you begin converging toward the center. The cosmic microwave background radiation, redshifted from your external perspective, becomes intensely blue-shifted as you fall deeper into the gravitational well. The temperature of this compressed radiation rises toward extreme values. What began as the cold afterglow of the Big Bang transforms into scorching heat that would incinerate any normal matter long before reaching the singularity. Time dilation effects also become more complex inside the horizon. While you experience normal time flow locally, the relationship between your time and external time becomes impossible to define. The outside universe effectively ceases to exist from your reference frame. But the strangest aspect of this inward journey involves causality itself. Information about your interior experience can never reach the external universe, creating a fundamental asymmetry in the flow of cause and effect. You could discover profound truths about the nature of reality inside the black hole, witness the breakdown of known physics, or encounter phenomena beyond human imagination. Yet, none of these discoveries could ever influence the external universe or benefit future generations. The interior journey also raises questions about the nature of space itself. If space-time ends at the singularity, what lies beyond? Does the concept of beyond even have meaning when space itself terminates? Some speculative theories suggest that black hole interiors might connect to other regions of space-time through wormhole-like structures. The mathematical possibility exists for the singularity to serve as a gateway to parallel universes or distant regions of our own cosmos. But these possibilities remain forever unverifiable. The event horizon ensures that any such discoveries would remain trapped within the black hole's interior, unable to communicate their existence to external observers. The journey to infinity represents the ultimate one-way trip, a voyage into realms of physics that may lie forever beyond human understanding. At the heart of Sagittarius A star lies something that breaks mathematics itself. The central singularity represents a point where the equations of general relativity admit their own limitations, where physical quantities become infinite and mathematical descriptions lose all meaning. However, this mathematical breakdown doesn't necessarily mean physics itself stops working. The singularity forms when matter gets compressed to infinite density, occupying zero volume. In this regime, the curvature of space-time approaches infinite values, creating conditions where general relativity can no longer provide meaningful predictions. Think of dividing numbers by values that approach zero. As the denominator gets smaller, the result grows larger without limit. At exactly zero, the division becomes undefined, breaking the rules of arithmetic itself. Singularities create similar mathematical breakdowns in the equations describing gravity. Physical quantities like density, temperature, and space-time curvature diverge to infinity, rendering calculations meaningless. But the existence of mathematical singularities doesn't necessarily imply that infinite physical conditions actually exist in nature. Instead, They likely signal the breakdown of general relativity in regimes where quantum effects become important. Most physicists believe that a complete theory of quantum gravity would resolve the singularity problem by describing what actually happens when matter gets compressed to extreme densities. Instead of infinite compression, quantum effects might create exotic states of matter or even bounce phenomena that prevent true singularities. String theory suggests that fundamental particles have finite size rather than being mathematical points. This could prevent the infinite compression required for singularity formation, replacing the singular center with a region of highly curved but finite spacetime. Loop quantum gravity proposes that space itself has a granular structure at the smallest scales. This quantum discreteness of space could prevent infinite compression by providing a natural limit to how tightly matter can be packed. Other theories suggest that singularities might be replaced by regions where space-time topology changes dramatically. Instead of infinite curvature, the center of a black hole might represent a transition point to regions with different numbers of spatial dimensions. The resolution of singularities has profound implications for understanding the ultimate fate of matter that falls into black holes. If true singularities don't exist, the information carried by infalling matter might be preserved in some exotic quantum state rather than being destroyed completely. But until we develop a working theory of quantum gravity, the nature of black hole interiors remains deeply mysterious. The singularity represents the boundary of human knowledge, a place where our most successful theories acknowledge their own incompleteness. For Sagittarius A star, this means that the ultimate destination of the matter it has consumed over billions of years remains unknowable. Whether this material gets crushed to infinite density, transformed into exotic quantum states, or tunneled to parallel universes lies beyond current scientific understanding. The mathematical end represents both a limitation of current physics and a promise of discoveries that await future generations of scientists. But even these unknowable cosmic monsters have finite lifetimes measured against the vast scales of cosmic time. Trillions of years in the future, when the last stars have burned out and galaxies have faded to darkness, Sagittarius A star will still be growing. Long after human civilization has been forgotten, long after Earth itself has been consumed by the dying sun, our galaxy's central black hole will continue its patient accumulation of matter. However, even black holes cannot escape the ultimate fate that awaits everything in our universe. The far future belongs to black holes. As stellar formation ceases and existing stars burn out, these cosmic monsters will become the dominant objects in a cold, dark universe. They will grow by consuming stellar remnants, planets, and the diffuse gas that permeates intergalactic space. But this growth phase cannot continue forever. Eventually, even the largest supermassive black holes will begin to shrink through Hawking radiation, slowly returning their accumulated mass energy back to the universe. The timescales involved defy human comprehension. Sagittarius A star will require approximately 10 to the 97th years to completely evaporate. This duration exceeds the current age of the universe by a factor of 10 to the 87th. To put this in perspective, if the entire history of the universe so far were compressed into a single second, the evaporation time for supermassive black holes would last longer than the current age of the universe, multiplied by itself trillions upon trillions of times. During most of this evaporation period, the black hole will appear virtually unchanged. The rate of mass loss through Hawking radiation remains infinitesimally small for objects as massive as Sagittarius A star. But the final moments will arrive with dramatic suddenness. When the black hole's mass drops to just a few times that of our Sun, the Hawking temperature will skyrocket, causing rapid evaporation and eventual explosive disappearance. The last second of Sagittarius A star's existence will release energy equivalent to millions of hydrogen bombs detonating simultaneously. All the matter that fell into the black hole over its entire cosmic lifetime will be converted back into radiation and elementary particles. This represents the ultimate recycling program. Every star, planet, and gas cloud that Sagittarius A star consumed will have its mass energy returned to the universe in the form of high-energy photons and particle pairs. But by the time this final explosion occurs, the universe will have expanded and cooled to temperatures just fractions of a degree above absolute zero. The violent death of our galaxy's central black hole will illuminate a cosmos so vast and cold that its energy will dissipate almost instantly into the cosmic void. Eventually, even the particles created by black hole evaporation will decay into photons and neutrinos. The universe will enter its final era, consisting only of elementary particles moving through ever-expanding space at temperatures approaching absolute zero. In this ultimate future, no structures will remain. No stars, no planets, no galaxies, and no black holes. Only isolated particles drifting through space that grows larger and colder with each passing eon. The monster that once anchored our galaxy and shaped the cosmic neighborhood where Earth formed will have returned its borrowed mass to the universe, completing a cycle that began with the collapse of the first massive stars over 13 billion years ago. Sagittarius A star's story represents both the ultimate triumph of gravity and its final defeat by the quantum nature of space-time itself. In the end, even the most powerful forces in the universe must yield to the inexorable expansion of space and the fundamental laws of quantum mechanics that govern reality at its deepest level.